Welcome to Lecture 2. We're going to be discussing SQL this evening. And a SQL does the same things that relational algebra does, but it's a different language, and obviously it will have a different syntax. Before we get into SQL, though, let's do a quick review of some important concepts. As we mentioned last lecture, tables and relations are mathematical sets, and therefore they're not supposed to have duplicate entries, duplicate entities, or duplicate rows in a table. And so we have the concept of a key that lets us establish a row uniquely. A super key is a set of fields in the table that when you take all those fields together, they uniquely define a record in the table. So for example, in the instructor table, the PeopleSoft ID by itself will uniquely identify a row in the table. Also, the PeopleSoft ID and the person's name in combination will uniquely define a row in the table. So both of those are super keys. A super key can become a candidate key if it's minimal. In other words, we cannot remove any fields from that list and still uniquely identify a row in the table. So ID by itself is a candidate key for instructor because we cannot remove any fields from ID and still uniquely identify a row in the instructor table. On the other hand, the list ID and name is not a candidate key because it is not minimal. We could remove name and we would still be able to uniquely identify each row in the table with PeopleSoft ID. So we can have several different candidate keys in a table, and one of the candidate keys is selected to be a primary key. The one that we select to be the primary key is selected for business purposes. And for example, if we have SSN, Social Security number, and PeopleSoft ID, both of those would be candidate keys, and we would probably choose PeopleSoft ID as our primary key because for business purposes, we want to limit the risk of identity theft and therefore minimize the use of Social Security number. Now, a foreign key is set so when we have tables that we want to join and we have a relationship between those tables, they can reference, the field in the one table can reference a field in the other table. And a foreign key constraint says that we will have to enter, we have to have the field in the referenced table when we put it into our referencing table. So it's just something that allows us to maintain referential integrity. We put a field in at, say, in an instructor, we say they're in the biology department. Well, referential integrity says you must have a row in the department table for the biology department. And that's what a foreign key does for us. Let's do a couple of relational algebra examples. Take a minute or two. And here's our schema. And we'll be using this for our SQL problems as well. So let's look at the first one. Given the relation instructor ID, name, department name, and salary. So this is our schema. And where salary is an annual salary, get the same information, but instead provide a monthly salary. Well, we can do arithmetic operations in our project and select operation. So if we take the instructor table, obviously we want to get the instructor salary, so that's going to be in our instructor table. So we'll use instructor as our table. Then we're just going to do a projection. We want all the rows, but we just want to give a monthly salary instead of an annual salary. So we project ID, name, department name, and then salary divided by 12. And that gives us a monthly salary. Let's take a look at the second one. Find the titles of courses in the computer science department that have 3 credits. So let's take a look at our schema. And we do have a course table, and the course table does have department name in it. And it also has credit hours in it. So we want to use our course table to get this answer. And here we're going to select only records that meet our condition. So the condition is computer science department. So department name equals computer science, and that have 3 credits. So credits equals 3. So this is our select statement. We use the sigma operator on the table course. And of course, we only want the title, so we'll use the project operator to project only the title. Okay, let's take one that's not part of our university system. Here we've got a table about a person whose hobby is collecting stamps, or people that might collect coins or do hiking. So we have various hobbies that we're going to include in our person table. And right now we've got 4 people in our instance. So let's look at what we get when we do a select statement on the person table, and hobby equals stamps. So hobby is the name of one of the columns. So we want hobby equals stamps. So that would be the first one. 1, 1, 2, 3, John, and so on. Stamps. Coins, no. Hiking, no. Stamps, yes. So that'd be 9876 Bart. So we move those 2 records into our output set. Well, we don't, the query optimizer does. And that's the result we get. So we'll start our understanding of SQL with some needed preliminary learning, and then next lecture we'll have a lot of hands-on exercises to reinforce it. You could probably benefit, though, by having your SQLite database engine using the university database to go through some of these exercises as I go through them in class. So let's go ahead and dig into SQL. Efforts have been made to standardize SQL, and probably 90% of the SQL written for Oracle will work on Microsoft SQL Server or MySQL or SQLite and so on. But it's not 100%. And the reason is that the standard came after the fact that we actually had these relational databases offered to customers. So Oracle and IBM and Microsoft built up large installations of customers who used their particular approach to SQL before there was a widely accepted standard that covered most of the functionality in the relational databases. And rather than have their customer base go back and rework the billions and billions of dollars of investment they had in the SQL that IBM and Oracle and Microsoft were offering at that time, they just maintain their way of doing certain operations. So these typically are going to be some of the more advanced type operations. The more introductory type SQL is probably going to be, for the most part, compatible across database engines. We're going to be studying sets today, And that's a case where there are some differences. Some systems use minus, others use except. So there are those kind of differences. But by and large, the SQL is it's portable between different vendors. So SQL lets us define tables, attributes, constraints, and other database infrastructure. And we can also use it as a query language where we access data in the structures we created. And it has some standard domains, characters and strings, integers, numeric values that can be used as currency, floats and real and double precision are the standard domain types in SQL. So to create a table, we have this syntax, create table R, and then we have attribute 1, domain 1. So in other words, we give the name of an attribute and what type it is. Is it a string? Is it a number? Is it a date? And so on. Then we have another attribute, because remember, our table will have multiple columns, or otherwise known as multiple attributes. So we define all those, and then we could put integrity constraints in so that we can further limit domains to specific ranges. And I gave as an example in our last class, we might have salary as a numeric domain, but we might want to have the range in that domain to be $20,000 to $100,000. So let's go ahead and we'll create something in SQLite. I'll first open up with a blank database. So I will share, we'll create this instructor table. Don't use your university database on this one. Just open up with a blank database. So I'll show you how to do that in my command prompt. Okay, so here we are. And I'm just going to type in SQLite 3. For those of you in Windows, you'll have to navigate to the folder where you put your database engine. So I start with SQLite 3, and I now have a blank database. And I can go .tables to show that there's no tables in my database. Operators preceded with a dot are not standard SQL. They are functions that are provided by the SQLite 3 database engine to let you do things like show what tables you have, show the schema of your database, things of that nature, quit the database, and so on. So let's go ahead, and I'm going to do header on and mode column, and that'll make the display a little more, a little easier to read. Let's go ahead and put in our create table instructor. We're gonna have a column called ID, column called name, another one called department name, and the last one, salary. And we have the types, you know, a fixed string, a variable strings. We have a not null, which means that we have to enter a value. We can't put null or no value in there. And of course, our salary, which is a numeric with 2 degrees of precision. And we'll just enter a record in just to show that's how we get data put in. So we have an insert statement, insert into instructor these values. So 10211 for the ID, Smith for the name, biology for the department, and the salary of $66,000. And now if I do tables, instead of no tables, I have the instructor table, and I can select some records from instructor. And there we get that one. Now let's test the not null constraint. So now I'm going to try entering a value with a null in there. So there's the null for the name. And of course, name is where we said it could not have nulls. So it does, the constraint is honored. And no matter where I try to put this in, application programs, utilities that we might write, no matter where it is, this constraint will be enforced. So we cannot enter something without a name, a record without a name. Okay, let's go back and learn a little bit more about integrity constraints. Not null, of course, means that it must be a value. There must be a value in that field. Null means no value. Primary key means that that is how we're going to uniquely identify our records. So we will not allow duplicates with a primary key attribute. And then a foreign key is where we're going to reference another table because we're going to be joining with that table, and we want to make sure it's got the values that we're putting in so we can match it up. So let's take a look at our instructor table. I'm just going to drop table. Instructor. Now we do dot tables, and there are none. And now let's create it again with some of these constraints in there. I mean, some of these additional constraints. We had a constraint in the last one. Okay, so now we've got our ID, name, department name, and salary, but we've defined ID as our primary key. So in this new table, because I deleted the old one, let's add our record in again. So we now have one record in the table. Now let's try and add another record with the same PeopleSoft ID, which is 10211. Oops. Oh, I've got the wrong kind of apostrophes there. Let's do this again. And we'll go like this. Okay, so we'll create our table. And come up. Okay, so now let's do it again. Yeah, the curly apostrophes are not standard ASCII, and so the SQLite shell doesn't like those. So those are all straight apostrophes. So we have that record added in. Now let's add in another one, and we'll collect this. So now we'll add Jones in, but Jones has the same PeopleSoft ID, and it comes back and it tells us that the unique constraint failed on instructor ID. That's because we already have that in our database. And we can show that by selecting a record from instructor. And there's Smith with that ID. Okay, so we can add these constraints in. Let's go back and learn more about SQL. So we have a create instructor like we did in a much more complex set of constraints. And we saw that we then could not add in duplicate values on the field that we defined as our primary key. Here's an even more complex set of constraints where we add in foreign key constraints. And that way, again, we make sure that the table that we're going to be joining to, for example, instructor might join to department, that department has the value of the department name field that we're giving the instructor, biology or physics or whatever it would be. Now here we can define our primary key. We defined it as a separate operation in the create table, but here a separate clause in the create table, but here you can add it to the definition of the primary key itself. So we say course ID varchar 8 primary key, instead of course ID varchar 8 comma, and then down below we have primary key is course ID. So either of those approaches is acceptable. A drop table is going to get rid of the table and all its contents. Delete from a particular table is going to leave the table. In other words, the schema will still be there so we can use it for new records, but it'll get rid of all the existing records. And we can also do an alter table where we can add columns, drop columns, so that we can enhance the or evolve the table over the period of its useful life to represent new requirements. So now let's take a look at our basic query structure for the select statement. And a select is where we're going to select a set of columns from the database or table that we want to display for the user. The from part is the tables that we're going to use to get those columns from, the data in those columns from. And then the where is the condition. So select A's, these A sub i's are the attributes. R sub i's are the tables. And then the P is the predicate. In other words, the condition that we use to select the tables. So why do we need a set of tables? Well, the attributes of a request from the user may not all be in one table. Because remember, we've split the information into uniquely themed entities. And so we have many tables, and we may have to join tables together, like join instructor and department to get information about the instructor as well as the department the instructor is in. So we'll go over in our next lecture joins and how we join these tables together. A natural join is a very straightforward way of doing that. But there's other approaches as well. So SQL queries are going to be very similar to relational queries in that you take one or more tables in your query operation and you return a temporary table with no name. So queries are, basically your database tables and the queries that go against them are by default case insensitive. They do have code pages and you can define case sensitivity, but that is when you're installing the database, that's one of the configuration options that you have. But plain vanilla, they tend to be case insensitive. So the select clause is how we're going to select information from our database tables. And the select clause, again, lists the attributes desired in the query, and it corresponds to the projection operation of relational algebra. Remember, this is a separate language, SQL. So let's take an example. Find the names of all instructors. So we would say select name from instructor. SQL names are case insensitive. Again, so you are going to have name equals name in caps equals name all lowercase. Now, as I mentioned, in relational theory, duplicates aren't allowed, and relational algebra will get rid of duplicates for you. By default, SQL does not get rid of duplicates for you because that's extra operation. And from a performance standpoint, back in the past, they decided that if you wanted distinct results, then you would have to say distinct. By default, they're just going to give you all the results. So let's take a look at this, how we would do that. It's instead of select department name from instructor, which gives us all the department names for all the instructors, and then we'd have duplicates. If we use the distinct phrase, then the distinct word in our select phrase, then we'll get a unique set. So let's take a look at this in our database. So we'll go back up and look at there. So I'm going to do a .shell, which lets me then use operating system commands. I'm going to clear this out. Then I'm going to do a .open umbc.db. Make sure I've got the right one. Yeah, so I do .tables, and that will show me the tables. .open and the name of the database, and that will open it. Obviously, you have to have the pathing information, but hopefully you're in the very folder that the database is in, and so you'll be right there. So let's do a select department name, and then from instructor, and you'll see that we get duplicates. We got computer science, finance, music, physics, history, physics again, computer science again, history again, finance again, biology, computer science again, and so on. So we get duplicates. Now let's add in the distinct word to our select phrase. And there we have the names of the departments without any duplicates. Okay, we'll go back to our lecture notes here. So an asterisk is used if you want to select all attributes. So when we say select star from instructor, that means give us all the columns. We can also perform arithmetic operations in our select, just as we did in relational algebra. So if we wanted to find the monthly salary for an instructor, we would say select ID, name, and then salary divided by 12. Now the where clause is where we specify the condition that records must satisfy in order for us to display them. And this, the where clause, corresponds to the selection predicate in relational algebra. So to find all instructors in a computer science department with a salary greater than 80,000, well, we're going to select the name from instructor. The instructor table is where the information is, where department name equals computer science and salary greater than 80,000. So the where clause is where we put our conditions. So let's take a look at that in SQLite. So here I've got my select statement, select name from instructor. And here's our where clause, where department name equals computer science and salary is greater than 80,000. And the result is Brandt. So that's the instructor who's in computer science and is making a salary greater than $80,000. So again, the where clause is where we put the conditions that are going to be important for our selection of records. The from clause is going to be where we list the tables that we're going to use to get information that we give to the user, because it's for the most part going to be the case that the information you need is not in one table. It's going to be in multiple tables, and you'll have to join those tables together. A Cartesian product is where you do a select star from multiple tables without any conditions. And that's going to give you every combination of records possible between those two tables. So you can get into astronomical numbers there. And we took a look at the Cartesian product in relational algebra, same thing in SQL. Joins are how we actually put records in one table and associate them with records in another table. So we've got the case where we want to look at all the instructors who have taught some course, find their names and the course ID of the courses that they have taught. So we would just look at our schema and we know, okay, we're going to have instructor fields that we'll need, but also course information as well. So we're going to select name and course ID from instructor and teaches. They taught some courses. The teaches table is where we would look for that information. And the teaches table has a field of ID, in other words, the ID of the instructor who taught the course. And obviously the instructor ID is going to have an ID for the instructor. So our condition is going to be where instructor.id equals teaches.id. So that will give us the records in the teaches table that have that ID value in their ID field. And then we'll get the name of the instructor and the course ID that they have taught for all instructors. Another example would be where we want to find the course ID, semester, year, and title of each course offered by the computer science department. So here we're going to select section.course ID. Now in this case, course ID is the same name in two different tables, section and course. So we have to specify which one we want. So we'll say section.course ID, semester, year, and title. The two tables we're going to use are in our from clause, section and course. And then in our where clause, we specify the conditions. Well, we want to match up on course ID. So the course IDs between the two tables must match up so that we get the section information associated with the proper course that it's a section for. And then we add a further condition that we only want the computer science courses. And so we would get, if we executed this, we would get the courses that we're interested in. So here's the schema for the university database. And we've got students with their fields. The underlined field is the primary key. Department name is the primary key. And notice that we've got a relationship between department name in student and department name in department. So we can match records up on those fields. Likewise with instructor. Then we have instructor and teaches. Well, in the teaches table, the primary key is all of the fields together. ID, course ID, section ID, semester, and year. In the instructor table, it's only the ID that is our primary key. So again, we can match on the instructor ID here to in the teaches table and just select out only the sections that were taught by a particular instructor. We have our sections, courses, takes is like register, what students have registered for, and then they've got their grade there. Classroom is where the sections are held. So a natural join matches the tuples with the same values for all common attributes. And by common attributes, that means attributes that have the same name. And it only retains one copy of each common column. So it gets rid of duplicate column names because obviously if they all share a common column name like ID, you're going to have ID twice. So they get rid of the one ID. So if we want to find the instructors and the courses that they have been teaching, we would do select star from instructor, natural join teaches. So let's take a look at that in SQLite. Okay, so we'll say, let's clear this out. And then we'll say select star from instructor natural join teaches. We can make that a little bit better. So let's do header on and mode column. Then we'll clear. When I say better, I mean easier to see. So we'll clear the screen, and then we'll do that again. Select star from instructor natural join teaches. And so we get each instructor, and then we have a record for each course that they've taught. So like Srinivasan has taught Computer Science 101, 315, and 347. Wu has taught Finance 201, Mozart has taught Music 199, Einstein, Physics 101, and etc. Okay, we'll go back to our lecture. So here's an example. List the names of the instructors along with the course IDs that they have taught. Well, that's the one we just looked at. But this slide is just to show you that there's multiple ways of accomplishing that particular activity. So the first one is where we select the name and the course ID from instructor, teaches, where, and then we manually define that matchup in columns. Instructor.id equals teaches.id. And that will give us the same result as the one we did, which is select name and course ID from instructor natural join teaches. I worked at Microsoft for 10 years, and Microsoft doesn't support the natural join because it's possible to get bugs in the natural join. So they just eliminated it, and you have to do things other ways. So one of the more common approaches is to use what we see here in the top select. So when we have complex queries, a strategy we might want to do is build it one step at a time. Start with a table that has a where condition, and then build on from there. If you need other tables, then put them in your from clause, and then add in the join conditions. And then you want to test your builds, and then obviously apply logical reasoning to the builds to make sure that they make sense, and then have a test harness that you can actually test the result to make sure you're getting a legitimate result. One of the most common things we'll be running into when we get into complex queries is we'll need to rename certain fields or tables. So SQL allows renaming relations and attributes using the as clause. So it's old name as new name. So for example, we were talking about monthly salary both in our SQL example and also in our relational algebra example. So in SQL, we can say select ID, name, salary divided by 12 as monthly salary. Then what the user will see is instead of salary divided by 12, they'll see ID, name, monthly salary. And that's what they want to see. They don't want to see salary divided by 12. Another thing we can do is use the as clause to rename tables. So here's an example where we might want to use that. Find the names of all instructors who have a higher salary than some instructor in computer science. So we'd say select distinct t.name from instructor as T. So we've taken the instructor table the first time and we've called it T. Then we're going to take the instructor table again a second time and we'll give it the title, the name S. So we want in our condition where T.salary is greater than S.salary. So that's going to be the salary in our T table is greater than the salary in the S table. So that'll give us the list of all the people that have a salary greater than someone. And then we also add in the condition and S.department name equals computer science. So now we're saying that we have people who are instructors and they have a higher salary than some instructor in computer science. Obviously, we're going to have string data in our databases. And so we have a full set of string operations that we can do in SQL. And some of the more common ones are we want to do wildcard selections. So with wildcard selections, we do the % sign, and that says match any substring. And underscore matches any character. So if we want to find all the names, all the instructors whose name includes the substring DAR, we would say select name from instructor where name is like, and then we have apostrophe, %sign DAR, %sign apostrophe. Like means that it doesn't have to be an exact match. It just has to be like this particular pattern. And of course, we have the escape character of / if we want to actually include a % sign in our match. Patterns are case sensitive. Some pattern matching examples, intro %sign matches any string beginning with intro. And then %sign comp, %sign contains comp. Dash, dash, dash matches any string with exactly 3 characters. And then dash, dash, dash %sign matches any string of at least 3 characters. And of course, we can do concatenation, upper lowercase, string length, extracting substrings, and so on. So sometimes our users will want to have our data displayed by a certain sort order. Like they might want to have the instructors sorted by name. Relational model doesn't care which order the records are in, so it's going to give them back to you in any order that it wants to. If you want it to be in a certain order, then you have to use the order clause. So we'll say select distinct name from instructor, order by name. And that will list the instructors in alphabetical order. And then you can sort on multiple attributes. For example, order by department name, and then within department name, order by name, instructor name alphabetically. Okay, so one of the other things we can use in our where clause predicates is the between. And that lets us simplify the number of conditions or reduce the number of conditions we have when we're doing salaries in a range. So if we want to find all the instructors with a salary between 90,000 and 100,000, then we would do select name from instructor where salary is between 90 and 100. And that'll give us those names. Okay, let's practice a little bit before we go on. Go ahead, take 5 minutes and find the names of all students who have taken at least one computer science course and make sure there are no duplicates in the result. So take 5 minutes, go through that, and then we'll look at the answer. Okay, let's take a look at this. Now there's, like as with any programming assignment, there's multiple ways to write a program to satisfy the requirements. So I'm going to show you the way that I did it, and obviously there's other ways of doing it. So let me bring up SQLite. So we want the information from the student table, the takes table taken, and course table, at least one computer science course. So those are our tables, and what we want is the name. So I'm going to select distinct name, and our condition is where, and this is where we're going to match up our requirements. So computer science course, so course.department name equals computer science. And now we've got the join conditions, and student ID equals takes ID, and takes.course ID equals course.course ID. And then we get the names that you see listed. Okay, let's go back. So again, looking at our schema, we have the student has an ID and takes has an ID, so we can match student and takes up. Then we can also match up student and course, because course has an ID and takes has an ID, so student takes course. Takes.course ID matches up with course.course ID. Student.ID matches up with takes.ID. And we'll go back and just take another look at this in our SQL, and we see there's our join conditions. Student ID equals takes ID, and takes.course ID equals course.course ID. And our other condition, non-join, is that we want the department to be computer science. Okay, we'll head back here. Okay, so our solution strategy, take the problems as goals, and then go forward with the schema, and where we can look at the attributes and tables as givens, and then look at our schema basically as a roadmap that we can use to help us solve the particular problem where we are assigned. This schema is going to show the relationships that we can use to connect different tables together, and then we connect together using relational operators, you know, and then between fields. Student ID equals takes ID. Takes.course ID equals course.course ID. Okay, and again, here's our okay, let's take a 10-minute break, and when we come back, we'll get into some more complex query operations.